Hello everyone, I am Chetan Sidling and welcome to this in-depth session on functional safety. Let me begin with a question. Have you ever wondered how your car's airbags know the exact moment to deploy in an accident, or why electric brakes keep working even if there is a software fault? These life-saving reactions are not luck, they are the result of functional safety. In this video, we are going to explore functional safety from A to Z. We will start from the basics, learn about the key standards, dive into the ASIL levels, understand the entire functional safety process, look at the real world automotive examples, learn about the tools and the technologies used, discuss challenges and the future of this field, and finally talk about careers in functional safety. Functional safety is the part of a system's design that ensures it continues to operate safely even if something goes wrong inside it. It's about detecting faults, responding properly, and preventing harm to people, the machine, or the environment. Take the example of automatic emergency braking in a car. If the radar sensor fails, the system must identify the fault and either slow the car safely or hand over control to the driver. This is how functional safety works, keeping things safe in abnormal situations. This is different from general safety, which includes items like seat belts, helmets, or airbags. Those are passive protective measures. Functional safety instead focus on the electronics, sensors, software, and control logic that must act correctly when fault happens. As vehicles, robotics, and machinery becomes more intelligent and software driven, functional safety is becoming increasingly important to save lives and build trust in technology. Functional safety became important after several industrial accidents that were caused by uncontrolled system failures. To avoid these tragedies, international standards were developed. The global foundation for functional safety is IEC 61508, which defines principles for electrical and electronic systems across industries. In automotive, the key standard is ISO 26262, which is a derivative of IEC 61508 tailored for vehicles. In industrial machinery, we use ISO 13849. In aerospace, standards like DO 178C and ARP 4754 ensure safety in both hardware and software. The process industry like oil, gas, and chemicals often follow IEC 61511. And for autonomous driving systems, a newer standard called ISO 21448, also known as SOTIF, Safety of Intended Function, deals with the risk not caused by failures but by system limitations. One key part of ISO 26262 is the concept of ASIL, or Automotive Safety Integrity Level. We will discuss this next because it's critical to understanding functional safety in cars. ASIL levels tells us how critical a function is to safety. The higher the ASIL level, the stricter the safety requirements. ASIL is determined based on three factors: severity, how serious the harm could be; exposure, how often the situation might occur; and controllability, whether the driver or system can control or avoid the hazard. There are four levels: SLA, the lowest level, used for systems with minimal risk; SLB, moderate risk, where a failure could lead to a minor accident; SLC, high risk, where failure could cause severe injuries; SLD, the highest and most critical level, where failures could result in fatalities. For example, interior cabin lighting might fall under SLA because it's not life critical, while airbag deployment or brake by wire systems are SLD because their failures can lead to serious accidents. SL guides engineers how much testing, redundancy, and fault detection are needed for each feature. Before we go deeper into the functional safety process, let's understand a few important terms. A hazard is a potential source of danger, such as unintended acceleration of a car. Risk is the likelihood that the hazard could actually cause harm. A fault is a defect in the system, like a broken sensor or a software error. When that fault causes the system to stop functioning as intended, it becomes a failure. Many systems are designed to be fail safe, which means that if something goes wrong, they switch into a a safe state. For example, if a brake system loses the electronic signal, it defaults to engaging the brakes to stop the vehicle. Some systems include redundancy, meaning they have backup components to take over if primary ones fail. Diagnostic coverage describes how effectively the system can detect faults, and latent faults are hidden faults that remain undetected for some time but could still cause harm later. The journey to achieve functional safety follows a systematic approach known as the safety life cycle. The first stage is hazard analysis and risk assessment. Here, engineers identify all the possible hazards that could arise in different driving or operating conditions. They assess how severe each hazard is, how likely it is to occur, and how easily it can be controlled. Based on this assessment, the ASIL level is assigned to each function. Next, engineers set safety goals, which are high level targets designed to prevent accidents. For example, one safety goal might state that the vehicle must be able to stop safely even if the brake sensor fails. Once the goals are defined, they develop a functional safety concept. This concept describes how those goals will be achieved. It might include adding redundant sensors, watchdog timers to monitor the software, or fail-safe mechanisms. Then they move to technical safety requirements, which define the specific hardware and software needed to achieve these goals. After this comes system and component design, where requirements are broken down into detailed specifications for ECUs, sensors, actuators, and software modules. Next is implementation, where the coding and hardware development happen. Once everything is built, the system goes through verification and validation, which includes several levels of testing such as unit testing, integration testing, and hardware in the loop testing to ensure everything behaves as expected in real world scenarios. Throughout the whole process, engineers build a safety case and documentation, which provides evidence that the product meets all safety requirements and complies with the standards. Let's look at some real life examples to see functional safety in action. Airbags must deploy at the right time during a collision, not too late, not too early, and only in specific situations. Electronic power steering must stay operational or switch to a safe mode in case of faults. Adaptive cruise control ensures the car maintains safe distance and prevents unintended acceleration. In electric vehicles, brake by wire systems need functional safety to ensure there is always a backup way to brake even if the electronics fail. Battery management systems rely on functional safety to detect overheating, prevent short circuits, and avoid fires. For autonomous driving features such as lane keeping and emergency braking, functional safety ensures the vehicle responds correctly even when sensors or software encounters faults. Developing functional safety systems requires specialized tools. Engineers use MATLAB Simulink and Stateflow for system modeling and simulation. For requirements management, IBM Doors is a popular tool. For testing, engineers use Vector Canoe and DSpace hardware in the loop platforms to simulate real world driving conditions. Tools like Polyspace and QAC perform static code analysis to catch software errors early. For safety analysis, techniques like FMEA, failure modes and effects analysis, FMEDA, failure modes, effects and diagnostic analysis, and FTA, fault tree analysis are used to identify and minimize risk in both hardware and software. Modern vehicles and autonomous systems are extremely complex. With thousands of components and millions of lines of software code, this complexity makes it harder to predict all possible failures and ensure safety. Cybersecurity has also become a major challenge because a security breach in a safety critical system could create a dangerous situations. Another challenge is balancing the cost of safety measures with market pressures to deliver product quickly. In the future, functional safety will increasingly rely on AI driven fault detection to predict and prevent failures before they occur. Standards like SOTIF will become even more important as self driving cars face unpredictable real world scenarios. We will also see functional safety expand to fields like electric aircraft, delivery drones, and collaborative robots, all of which needs reliable safety mechanisms for human interaction. Functional safety offers excellent career opportunities for engineers. There is a high demand for professionals in industries like automotive, aerospace, railways, industrial automation, and medical devices. To build a career here, you will need a strong foundation in electronics, embedded systems, and control systems, along with knowledge of standards such as ISO 26262. Hands-on experience with the tools like MATLAB Simulink, Canoe, and IL testing is also essential. You could start as a functional safety test engineer, verification engineer, or safety analyst and progress to roles such as safety manager or consultant. With the growth of electric and autonomous vehicles, this field promises an exciting future. In conclusion, functional safety is more than just meeting regulatory compliance. It's about saving lives and building trust in modern technology. As machines and vehicles become smarter and more connected, functional safety ensures they remain safe under all conditions. I hope you enjoyed this detailed journey through functional safety. If you found it helpful, don't forget to like this video, share it with your friends and colleagues, and subscribe to my channel for more content on automotive electronics, embedded systems, and safety engineering. Stay curious, stay safe, and I will see you in the next video.